You ever look at a bunch of data points scattered on a graph and just wonder, how in the world can I make a smart guess from all this chaos? Well, that's the exact prediction puzzle we're going to solve today, and we'll do it using a really cool tool called linear regression.
So here's the central mystery we're diving into. We're staring at this cloud of data, right? And our mission, should we choose to accept it, is to find the one single straight line that slices through it all in the best way possible.
Okay, to make this feel less like a math problem and more like, well, a real problem, let's look at this chart. Down at the bottom, we have a person's income. And going up the side, that's how much they spend on food. Every single dot is a different household. You can already kind of see a pattern, can't you? The more someone makes, the more they tend to spend on food.
And that brings us to a super practical question. If some new person walked up and told us their income, could we use this data to make a decent guess, a prediction, about what their food budget looks like? I mean, how would you even start?
And this right here really shows you the problem. You and I could just start sketching lines that seem to, fit the data. We could draw a steep one, a flat one. Some seem to hit a few more dots than others. It's a mess. So yeah, that is the million-dollar question, isn't it? Which of these lines is truly the best one? We can't just eyeball it and say, that one looks good. We need a rock-solid mathematical way to find the one line that is, objectively, the absolute best fit.
All right, so to find the best line, we first need a way to keep score. We need some way to measure how good, or, how bad, any particular line is. And let's call that measurement our error. So here's how we're going to do it. For any line we try to draw, the error for a single data point is simply the vertical distance from that actual point down to our line. It's the gap, right? The gap between what really happened and what our line predicted would happen. And this little gap, this error, it actually has a technical name. It's called a residual. It's a really simple idea, but it's super powerful. A big residual means our line made a terrible prediction for that point. A tiny residual means we were pretty darn close. So, logically, it seems pretty straightforward. If we can measure the error for every single point, we can just add it all up. And the line with the smallest total error, the one that minimizes all those residuals added together, that must be our best line. Simple, right? Well, maybe not as simple as it sounds.
Okay, so this is where our little investigation hits its first major twist. Because that super obvious idea we just had, it's actually going to lead us completely down the wrong path.
Let's just try it. What if we try to find a line where the sum of all the errors, all those residuals, just adds up to 0? I mean, a total error of 0 sounds perfect, doesn't it? What could possibly go wrong?
All right, let's put this to the test with some really simple data. We've got just 4 points, and we're going to try fitting this line, y equals 4x minus 4. It looks okay, I guess, but let's actually check the numbers. Okay, let's walk through the table. For that first point, our line nailed it, residual of 0. Perfect. For the next one, our line predicted 8, but the real value was 6, so that's a residual of -2. For the third, our line predicted 4, but the real value was 6, so that's a +2. And when we add it all up, yep, we get 0. It seems like we found it, our best line. But wait a minute. Let's try a totally different line. How about a completely flat one, just y equals 6? Now this line looks nothing like the first one. It doesn't really seem to follow the trend of the data at all.
Let's run the numbers one more time. The prediction is always 6. So for the first point, we get a residual of -2. For the last point, a residual of +2. And the two in the middle are perfect fits. So the total sum is, oh boy, it's 0. Again.
Okay, this is a total disaster. Our method just told us that two wildly different lines are both the best. The problem is clear now, right? The positive errors and the negative errors are just canceling each other out. So this method, it's a failure. It's a bust. We need a much better way to do this.
And that brings us to the real hero of our story, the elegant, correct, and actually pretty simple solution to our puzzle. This is the breakthrough moment.
So, how do we get around this whole cancellation problem? How do we stop the positive and negative errors from wiping each other out so we can find the one true line with the smallest possible error?
And the answer is so simple, it's absolutely brilliant. We just square every single residual. Before we add anything up, we multiply each error by itself.
This one little move does two incredible things for us. First, it gets rid of all the negative numbers. A residual of -2, when you square it, becomes a +4. Problem solved. Second, and this is really clever, it punishes big mistakes way more than small ones. An error of 3 squared is 9, but an error of 10 squared is 100. It makes our line really try to avoid those big misses.
And this powerful, elegant technique has a name you've probably heard of: the least squares method. We're not just finding the line with the smallest sum of residuals anymore. Nope. We're finding the one unique line that has the absolute minimum sum of the squared residuals.
Okay, so let's zoom out for a second and put a formal name on this whole process we've just figured out. This whole thing, from start to finish, is called simple linear regression. It's just a mathematical model that gives us that perfect straight line equation, y = a + bx, that does the best possible job of describing the relationship between our two variables, like income and food spending.
And let's quickly decode that equation. Y is the thing we're trying to predict. X is the data we already have. And the model's job is to calculate two magic numbers for us: A, which is the y-intercept, that's just our line starting point, and B, the slope, which tells us how steep the line is.
And this is the final, most important connection. Those two magic numbers, A and B, they're not just guesses. The least squares method we just uncovered, that is the engine under the hood that crunches all the numbers and finds the single perfect values for the slope and the intercept that gives us our one true best fit line.
So, we've solved it, we've cracked the puzzle. We now have a foolproof method for finding the single best predictive line through any cloud of data. But, and this is a really big but, just because we found the best possible line, how do we know if that line is actually any good? I mean, is it really useful for making predictions in the real world? Well, that's a whole other mystery for another time.